Hi everyone, in this video I'm continuing to work through question 13 part C of the 2020 North Sydney Boys Extension 2 trial exam. So in prior videos I've worked through part 1 and also started working through part 2. So if you haven't seen those prior videos already, definitely take a look, because in this video what I'm doing is I'm continuing to think about how we can tackle part 2. So part 2 wants us to find the area of the rectangles, the shaded in rectangles that are sitting beneath the curve that we're dealing with. And in the video immediately prior to this, we looked at an example for a particular value of n. So now what we're going to try and do in this video is generalize that result for all values of n where n is an even number. So let's take a look. So I've recreated our diagram here. Again, my semicircle is quite wonky. Ideally it would be perfectly symmetrical, but hopefully it won't hinder our ability to think about what the general result should be. Now if I just go back to the prior working, we looked at the case of n is equal to 4, 4 being an even number. So that gives us an example of an even number. But what we want to do now is look at the whole case, I'll call it case 1, where n is any even number. So what we want to do is think, well, what are some of the elements of what happened here when n was equal to 4 that we know will continue to happen in general for any even n? And I think the first thing worth noting is that our first and last rectangles will still be nothing, like they'll have a height of 0, because if we're thinking about the rectangles that are beneath the curve, then these first two, for them to be beneath the curve, they have to have no height. So we kind of know we're going to have nothing here and nothing here. That's the first thing to note. Now the next thing to note is if we're taking this range between 0 and 2 and dividing it by an even number, then you know that you're always going to have a line that lands exactly halfway between, because you're almost cutting it in half and then cutting it in half again and cutting it in half again. Through that process, that's how you get an even division. And so we know, another thing we can know for sure, if I just get my ruler, is that there will be a line here at 1. And just like it was the case when n was equal to 4, whilst we have that line, it itself won't form the height of a rectangle. The rectangles will be around that line. So we need to think about that, because remember, when we were working through n is equal to 4, we effectively ignored that. We didn't actually do a calculation of 2 over 4 times f 4 on 4. We skipped over it because it didn't form part of a rectangle. So what we're going to have is we're going to have that line, and then we're going to have some rectangles around it. Now I'm just going to put a dot, dot, dot there, because we're dealing with a generic n, so we don't actually know how many rectangles there will be. But I guess in terms of a pattern, what we do know is that after this rectangle of no height, we'll then have a rectangle at the point, well, this distance will be, in generic terms, 2 divided by n, because we're dividing this whole range into n equal parts. And then we'll have a line coming up here, and so this is the rectangle that will form beneath the curve. So that's the first rectangle that we're going to care about. And then we'll have a line, in theory, coming up here, and so this will form the next rectangle. And basically so on and so forth, all the way until we get up to our point 1. And then you kind of repeat the process, but you can almost go from 2 the opposite direction. So you'll come up here, and you'll have this point. And it's worth noting that this point is, well, if this is 2 on n, so this would be 4 on n, 6 on n, and so on. And this would end up being 2n on n, and that's how you get 2. So the one before that would be 2n minus 1 on n. That's how many you've gone, kind of 2 on n, n minus 1 times to get to this point, this last point before the 2. and then we'd have this point, and so you connect that to get a rectangle, and again they should be at the same height in theory because it's meant to be symmetrical, but again that's just my poor drawing. So there's a rectangle, and then again you'd kind of have a line up here at this point, a rectangle. And hopefully you followed along there in terms of what's happening in general. We're dividing the range into 2 on n. Because we're concerned with the rectangles beneath the curve, the first and last rectangle still effectively have a height of nothing, just like what happened when we were dealing with 4. And then we have rectangles that kind of come towards this point 1, the exact midpoint of the range, but that point 1 itself doesn't form, there's no rectangle there. So if we now think about, okay, well, what is that in general? What's happening? In general, the area we can write as, it's going to be, again, we're going to have this first rectangle will be a width of 2 on n. And at this point, the function is f at 2 on n. And then again we'll have another rectangle with a width of 2 on n, and the height of this rectangle will be the function at 4 on n, because we've gone 2 on n 2 times at this point. And then you'd keep going, and in theory what I'm going to do here is I'm going to say, let's pretend there is a rectangle at this exact midpoint, so the function n on n. Now we know there isn't, but let's just pretend there is, just so that we get this consistent 2, 4, 6, 8, 10, 12 and so on, all the way up to the midpoint. And then we're going to keep going, we're going to keep with that pattern, always moving up in a 2 on n, until we get to our last rectangle that we know will be 2 on n times the function at, in this case, 2 n minus 1 on n. So that's kind of all the rectangles we know about, plus this extra rectangle that we kind of know isn't really going to be there, but we just want it so we can get this consistent sum. So what we'll have to do is we'll just have to subtract that off the n. So we'll go minus 2 on n, f of n on n. Just to make really clear, actually, if I'm going to add that in, because I know there's no rectangle there, so I don't need to be multiplying it by this width, I'm just going to take it off at the end. Now, the benefit of doing that is this first part here, we can write in sigma notation. And the way we know that sigma notation is going to be helpful is when we eventually get to part 4 of this question, we're going to see that it's all kind of linking together because we're trying to show the limit of a certain summation. So I think the next natural step here is to think about how we can write this in sigma notation. So I'm just going to write this as, I'll factor out all these 2 on n's, and then we'll multiply that by, I'll just put this in brackets so we can help eventually distinguish it from this. So we're going to have the sum from k, so I'll write r. Normally I would write k, but I noticed that in the question, again in part 4, in the sigma notation they use, for whatever reason they used r as the variable. So I'm just going to use r again to be consistent. But actually, it shouldn't really matter what letter you pick. You can pick any letter you like, just don't pick n, because we're already dealing with n. But here, I'm just going to pick r, so we're going to have the sum from r is equal to 1 up to n minus 1, I'm going to pick, because we're essentially doing this n minus 1 times. And what are we doing? In each time, we're doing the function at, if r is equal to 1, this would be 2r on n. Every time. So if we think about what that is, it's 2 times 1 is 2, so it's 2 on n. 2 times 2 is 4, 4 on n. 2 times 3 is 6, 6 on n, and so on. And then we're going to end up with 2 times n minus 1 on n. So you can see how that works. That's just our shorthand way of writing this in sigma notation. And then we don't want to forget our minus 2 on n f of n on n at the end. All right, so now we've got to do the work of actually kind of simplifying all this. And again, we don't really want to leave it in this function notation. I think it's not incorrect, but again, because if you take a look at the question and kind of read ahead to part 4, you kind of see the kind of format of what ultimately we're working to. And so I think it makes sense that we take this function, which we know is the square root of x to the 2 minus x, and we insert this. So wherever we see x, we put this, and see what we get. And same deal here, wherever we see x, we put n on n, which is just 1. So we just put 1 in and see what we get. So this is going to be equal to 2 on n times, we're still dealing in sigma notation, so the sum from r is equal to 1 up to n minus 1 of the square root of x, so 2r on n, bracket, 2 minus 2r on n. So that's the first thing, minus 2 on n times f of 1, since n on n is 1, so it's going to be the square root of 1 times 2 minus 1, which is also 1. So it's really the square root of 1, which is just 1. So now if we think about simplifying this, we'll get equal to 2 on n times, so how can we clean this up? Probably worth getting a common denominator here. So it's the sum from r is equal to 1 to n minus 1 of the square root of 2r on n times 2n minus 2r on n. And then this just becomes minus 2 on n, since that simplifies to 1. So, okay, let's see what we're dealing with here. This will be 2 on n times the sum from r is equal to 1 to n minus 1 of, we can factor out a 2 here, so this 2n minus 2r, we can bring out that 2, so we'll have the square root of 4r, and then we'll just have n minus r, and these n's can come together to give n squared, minus 2 on n, we can't forget about that 2 on n that drops off. Maybe worth turning over here so we don't run out of space, so let's turn over and say the area is equal to, and let's see, so we've got, maybe I'll square the top and bottom, that's probably a good next step. So I'm going to be quite deliberate to do this one little step at a time, just so we don't make any mistakes. So we've got the square root from r is equal to 1 to n minus 1 of, so if I square root the top, we're going to have the square root of 4 times the square root of r n minus r. So square root of 4 times the square root of r n minus r. And then divide that by the square root of n squared, which really, square root of n squared is just n. So we can just put an n down here. And then minus, always remembering this minus 2 on n, sitting off the end. Now in terms of cleaning that up, the square root of 4 is just 2, and I can bring that out actually. So it's equal to, 2 times 2 would be 4. And in theory I can bring out this other n, so we get 4 on n squared times the sum from r is equal to 1 to n minus 1 of the square root of r bracket n minus r, and then minus 2 on n at the end. So I think that is the result. Now again, I've mentioned a few times that you can kind of read ahead to part 4 of the question where you can see what we're ultimately finding the limit of, and it's quite similar to this. The only difference is you'll notice that this n squared has been put inside the summation. So actually, if you could stop here and say, and you'd be totally fine, but you could also, if you wanted to, thinking ahead to part 4, just throw the n squared in. So you could say 4 times the sum from r is equal to 1 to n minus 1 of the square root of r n minus r on n squared. The n squared, from the perspective of this variable r, is just a constant, but it doesn't matter whether it's inside or outside the summation, you still get the same result. And then minus 2 on n. So that is the generic area of the rectangles that will be formed when you divide this range 2 into n equal parts, but only in this case when n is even. That's what happens when n is even. So actually we now need to think about all of this again, but when n is odd, to see is it different? Is it the same or is it slightly different? And again, it's probably going to be no surprise that it is slightly different. And that is why we need to go through this process again. So what I'm going to do in the next video is very similar to what I did for this first case. I'm going to pick a value of n. It probably makes sense to do n is equal to 5. See what we get, and then we can check. And actually, that's something I haven't done yet. We can now verify, before I wrap up this video, let's verify this result here. Let's check it for when n is equal to 4, because if I substitute 4 in here and I don't get the square root of 3 on 2, then I'm in trouble. But if I do get the square root of 3 on 2, that gives us comfort that we've worked through this correctly. So let's check. So when n is equal to 4 in this formula, what is the area? It's equal to 4 times the sum from r is equal to 1 to 4 minus 1. So from r is equal to 1 to 3 of the square root of r4 minus r, and divided by n squared, or 4 squared, so divided by 16, minus 2 on 4. Alright, so let's now work through that. What I might do is I might just bring out the 16 just so I don't have to keep writing it. So it'll be 4 on 16 times, and now we want to throw in all the r is equal to 1, 2, and 3. So we'll have the square root of 1 times 4 minus 1 is 3, plus the square root of 2 times 4 minus 2, or square root of 2 times 2, plus the square root of 3 times 4 minus 3 is 1, so 3 times 1. And then minus this 2 on 4 at the end. So it's going to be 4 on 16 times the square root of 3 plus the square root of 4, which is just 2, plus another square root of 3, minus 2 on 4. And I guess I should try and simplify this to get root 3 on 2 rather than just throw it in my calculator. So what do we got here? We've got 4 on 16, which is 1 on 4. And we've got 2 root 3's plus a 2. And then minus a half over here. So what is that? If I just put this through, it's going to be 2 on 4, or 1 on 2. So it's going to be root 3 on 2, plus 2 on 4, or plus a half, and then minus a half. These two halves cancel. So yeah, we get root 3 on 2, which is what we got when we had n is equal to 4. So that doesn't necessarily prove that we've definitely got it right, but it at least provides some comfort. I mean, if we got a different number, we know we're in trouble. But because we got the same number, it gives some comfort that this result is probably right, at least for the case where n is even. Alright, so hopefully you followed all that. I think quite tough actually, and we're not even done yet, which is why I suspect whoever wrote this question maybe didn't anticipate that you need to do 2 cases, because if you only had to do this one case, if for example in the question they said do it when n is even, I mean, this is still a lot of work for, I think it's 2 marks. Let me just check actually. Yeah, 2 marks for all of this. I mean, that's yeah, that's pretty rough, especially given we're about to do it all again. So yeah, I just suspect whoever wrote this question maybe hadn't fully thought it through. Yeah, so what I'm going to do in the next video, I'm going to go work through n is equal to 5, see what we get, and then in a follow-up video to that, I'll then try and generalize the result. All right, tick boom.